All right, hello and welcome to a new set of slides on a topic called Boolean Algebra. It's actually really nice. It's essentially just the logic slides all over again, so everything that I talk about is going to sound very, very familiar, so enjoy that. So Boolean Algebra, what it is, it's just a bunch of rules and operations, because that's what normal algebra is, right? It's just a bunch of ways of solving equations and stuff and using variables. Well, Boolean Algebra is when you're using Boolean variables and Boolean values. So a set of rules and operations for working with variables whose values are either 0 or 1. And so this legitimately is the logic slides all over again, because 0 is false and 1 is true. Let me write that a bit cleaner. So that's fun. Yeah, so you technically know all of this already. That's exciting. Because 0 is false, 1 is true, and the AND operation, that's going to be multiplication in Boolean algebra land. The OR operation is going to be written as plus in Boolean algebra, but it's going to do the same thing. And then negation, instead of putting like this not symbol, you're just going to put a bar on top of your variable and call it the complement instead. All right, it's all the same. So like if you see in Boolean algebra 1 times 0 equals 0, that's just saying, this is equivalent to, right, true ANDed with false is equal to false. Yeah? And there's a reason why they chose the multiplication symbol, because this really is 1 times 0. It really is 0, isn't it? So multiplication is kind of AND. That's pretty cool. So yeah, Boolean algebra, we're working with values 0 and 1. That's what our variables can hold. It's just true and false all over again, though. Let's see. Literals is just a fancy word for the variables inside of your Boolean expressions. It's a Boolean variable, or its complement. So like x, y, x bar, y bar, those are literal values, we say. And then, yeah, let me just show you some operations again, like 1 ORed with 0. 1 plus 0 is 1. One weird, and that's kind of like normal arithmetic, but it gets a little weirder, right? Because 1 inclusive ORed with 1 is still 1. So that doesn't make as much sense as maybe it should. And then negation, not false is equal to true. 0 bar is equal to 1, right? So that's how that's working. And yeah, so that's literals are just single Boolean variables, and then min terms, we call those for a weird reason we'll get into later. A min term is a product of literals. So a bunch of variables or their complements, if you multiply them together, so you're ANDing them all together, those are min terms, all right? Stuff ANDed with stuff is very, very important to us. So all of these things are min terms. Even variables by themselves technically count as min terms, but just a bunch of variables, maybe their complements too, multiplied together, this is a min term, all right? So that's just the notation, the terminology, and there's plenty of fun memes. Please feel free to pause and enjoy this one. But I have plenty more where that came from. So yeah, a new place that we would like to go is, because this is essentially logic all over again, I would like to teach you about how to kind of make circuits for these things. Because at the end of the day, we're trying to do all this stuff inside of a computer's processor. Like, that's the reason we talked about the AND operation, the OR operation. Like, if we had a computer that could do AND really fast, that could do OR and complement really fast, then we could compute anything that ever needed to be computed. So that is the goal. And so here is, let's learn how to make schematics that build up large computations in terms of Boolean algebra. All right. So you can translate all Boolean algebra operations, which are just logical operations. You can translate those into physical hardware, where like you're sending a 1 along a wire and a 0 along a wire to this box, and that box is performing the OR operation, and it spits out 1 because, of course, the 1 ORed with 0 is still 1. So that's the game that we're going to play here, and there are some fun links. Feel free to click on them. That lets you like draw these circuit diagrams a bit easier, so you don't have to like write it on paper and like watch how they work on particular values. So try to use the circuit simulators if you would like, but I'm going to teach you these different logic gates, we say. All right, so let's learn about all the different circuits that we can make. It's just essentially a blueprint of how you want to execute a Boolean operation. And this will make sense with an example, I promise, but we got to get there first. So these are the gates that you will see. Oops, I forgot to delete some extra things. I'll draw it right back. These are the main logic gates, we say, that you're going to see most likely. It's the AND gate, all right, the AND gate, and that's going to take two wires, two input wires, and one output wire. So X and Y come in, and then it multiplies them or ANDs them together on their way out. And so like this one looks like, I don't know, the bullet from Super Mario, and there's like an AND symbol going on in there. So that is the AND gate. The OR gate is like a curvier version of that. That's how you differentiate between the two. But again, you have two things coming in, two wires coming in, and then output is their sum, or their OR. This is an OR gate, and then this is a NOT gate, or an inverter, we say. So you have X coming in, and then it inverts it, and you have like NOT X, or X bar coming out. Okay? So inverter, you can also call it a NOT gate. And to help you understand future gates, you can think of like the negation happening at the dot. All right, that'll help you understand fancier gates that also do some negation and some other things. So yeah, AND gate, OR gate, and the inverter or the NOT gate, those are the ones we're really going to care about because you can do anything in terms of those. All right, so here's an example, and let's walk through it. So first of all, here's a fancy gate. Definitely go back to this slide and try and understand it. What is the output? Let's try and figure out the output of this gate when X is 1, Y is 0, and Z is 1. So these are the inputs on the left here, and we're going to pretend that X is 1, Y is 0, and Z is 1. This is just another way of writing some complicated logical expression, and we're going to break it down slowly but surely. All right? So what in the world are we trying to do here? So 1, 0, those are taken into an OR gate. This symbol is just like we're duplicating X and it's jumping along the wire. It's not counting towards Y. So this is ORing, right? This is an OR gate taking X and Y. See, it's an OR gate. And so its output is going to be whatever X ORed with Y is, and that's going to be a what? It looks like it's going to be a 1, right? It's going to have a 1 there, and that's what's coming out along that wire. And then similarly, like this is taking X, jumping over this wire, and then it's inverting it with an inverter. So coming out of this wire is X bar or like 0. So that's the negation of X. And this is the negation of Z for the same reason. There's a 1 there. And all right, these are getting ANDed together. How do you AND a 0 or 1? Then, well, it's just a 0 because they're not both true, and then we're ANDing together, now a 1 and a 0. So this all turns out to be 1 ANDed with a 0, and remember that these are AND gates. Our final answer is 0, or false. All right? So that is why that is the output. The output is in fact 0, because it's computing, well, X ORed with Y, so let's do the Boolean algebra notation, 1 plus 0. And then it's doing this stuff. It's taking X and negating it, and taking Z and negating it, and ANDing those things. So it's taking X. It's like, here's X negated, so 1 bar. And then it's taking Z, which is 1 bar negated, and it's ANDing them. And then it's taking these two results, and it's also ANDing them. So like a multiplication is going on there. And so that becomes... like we said, this is all equal to 1 or 0 is just a 1, ANDed with 1 bar, which is 0, ANDed with another 1 bar, which is 0, and so the final answer is 0, and that's why we got that, all right? And now you can ask the question, like, what is the formula that this is representing? What is the Boolean formula? And let's write it in terms of like our ands and ors, and then also our pluses and minuses and pluses and timeses and bars too. All right, so what's the Boolean formula that this is trying to compute? Again, you can just walk through it. Like this is taking X and Y and ORing them. So coming out of this, it's X or Y. Oops. X ORed with Y is coming out along this wire. Right here, this is not X. Right here, this is not Z. Coming out of this is their AND, so not X ANDed with not Z. But let's see here. That's fine. And then coming out of all that is X ORed with Y, and then all that ANDed with, right, because we're ANDing the other side, ANDed with this thing. ANDed with not x and not z. And I don't have to draw parentheses because of the associativity of AND. All right, so that's the output. And so this is the Boolean formula. It's x ORed y and not x and not z. And of course, this is equivalent to our new notation, this one right here, plus multiplication and complement. So we got x plus y for x or y, and then multiplication for and not x, so x bar, ANDed with x bar, ANDed with z bar, right? So those are equivalent ways of writing the same thing. This is just an older style notation, I would say, right? So with that in mind, maybe you'll want to go back to these slides and study this example. You try. So here is a Boolean expression written in the new style. Draw a circuit diagram for it. See if you can get that with the AND gates, the NOT gates, the OR gates, whatever you need. And then, once you have it made, go and evaluate it too. When x is 1 and y is also 1, and then when w and z are both 0. So give that a try. Alright, so assuming you've got it down, let me show you how I think about this. So I try to break it down to the smallest stuff first, like this. Like this is kind of the last operation, this OR. It's like do this thing, and then OR them together, right? So let's work on the smaller things first. So here's x ANDed with not y. You see that? So x times y bar is x ANDed with not y. So I have my wires, right? I have my input wires x and y. To compute the AND of x and y bar, I need to invert y. So I need to use a NOT gate. I need to use an inverter here. And so now, coming out of this wire, I have not y. All right? And then I can, with x, pair it together with an AND gate, finally, to do what I wanted to do with it. I want to compute the AND of those two values. So I use the AND gate there. And so this now has x and y bar coming out of it. Okay? And you can do the same thing with this stuff on this side. It looks like it's involving z and this is w plus z, all of that done at once, and then barred all of that. You see how it's negating the whole thing? Looks a bit weird, but that's how that's working. So yeah, in order to get at that, I guess we need a z on one side, and then we need a w or z bar first. So maybe we can work with that. Here's a w, here's a z input wire, and let's start with this side. W or z, we need to negate that. So let's compute that somehow. So w or z, we got to do that first, and then we're gonna negate it. So we'll send this to an OR gate. Maybe I'll get these wires closer to each other. An OR gate is curvy like this. There it is. And now, so this has w or z, or w plus z coming out of it. We need to complement that with an inverter. Take whatever that is and invert it. NOT gate. And so now we have w plus z all bar, and I want to AND that with z still. And so I'm going to have an AND gate, of course. And let's see here. The order doesn't matter. AND is commutative, so I'll put the w and z up top here, or w or z bar, and then I'll take another z here, maybe out of this. I'll make a little dot and say, here, take it again, copy it. And then I'll bring it in here to an AND gate. And so now coming out of this, I finally have, let's see, that's z ANDed with w plus z bar. That's fun. So that's a lot coming out there. And then finally I have the x and y bar, and I have the z and w or z bar, or w plus z bar. Now I need to OR those two results together. You see how that's working? And so one last OR gate will take care of it. And this is just a graphical representation of how your Boolean formula is going to give you an answer, how this equation works. And so this is the final thing. This is finally your x and y bar ORed with z ANDed with w plus z bar. Okay, so now that we have that, now that we know what it is, you can draw it. Probably might be easy to draw like ones and zeros and watch them be passed along, or you can just do it in this form, whatever is easiest for you. Let's evaluate it when x and y are 1 and w and z are 0. So if x and y are 1, it's 1 ANDed with 1 bar, plus a z, which is a 0, ANDed with w plus z bar. So that's 0 plus 0 bar. All right. So let's see. 1 ANDed with 1 bar. That's 1 ANDed with 0, which is 0. And then we OR that with 0, and technically we don't need to do this over here because anything ANDed with 0 is 0, but let's do it for fun. This is going to be 0. 0 ORed with 0 is 0. Negate that, bar it, complement it, that gives you a 1. So it's 0 plus 0 times 1. And that is equal to 0, of course. False. So false ORed with false ANDed with true. And this was kind of binding tighter. We do that one first. So that's the idea, and the answer is 0. I hope that makes enough sense to you, and that's what you got too. Okay, so yeah, that's Boolean expressions. It's really just a new notation for something you already know. It's not too bad. And so here's another meme, and please enjoy that as I look at my notes for what to do next. So yeah, let's get to this idea of min terms. Like, why in the world did anybody come up with this word, and why is this important when you have a bunch of literals either like ANDed together? Why is AND so important? Well, let me show that to you. There are some forms that you would like to eventually get your Boolean formulas into. That would make your life a whole lot easier. So there's two kinds of normal forms for Boolean expressions that you would like to convert your Boolean expressions into if you can. The first is called disjunctive normal form, or DNF for short. It is a sum of products of literals, and so that means it's a bunch of min terms together, right? Products, and then a sum of those. So the outermost thing is an OR. So here's some examples of disjunctive normal form, DNF. It's you have a bunch of products, which are, I don't know, I'll write it down here. I'll write it up here first. You have a bunch of products of literals, so like x times y bar times z, and then you can have as many others as you want. That's a product of literals by itself. That works. P times q bar. So that's a bunch of products of literals, and then a disjunctive normal form formula is a sum of those things, so plus at the outermost level. All right, so that's what's going on there. And so this is, of course, equivalent to x ANDed with, not y, ANDed with z, ORed with, just w, ORed with, p ANDed with, not q. All right, so this is a sum of products. It's an AND of ORs. That's disjunctive normal form. The other kind, and remember that these are min terms. It's a sum of min terms, essentially. That's how you can remember DNF. And then CNF is kind of the opposite. It's called conjunctive normal form, and it's a product of sums instead of a sum of products. All right, so the outermost operation is and that is called conjunction, just like OR is called disjunction in the fancy logical math places. Okay, so here are some examples of CNF. It's an AND of OR, so like if I just flip all of these to be like x ORed with, not y, ORed with z, and that with w, and that with p OR, not q, that's immediately CNF. All right, I hope that makes sense. And then, again, we can do the fancier style where it's like p plus q, that's like the inner thing. It's a bunch of sums. This is like x plus y bar, and I don't know, z plus w, and then you and them together, so it's a product of sums. That's conjunctive normal form, and of course we can translate this back to the logic that we know and love. P ORed with q, ANDed with x ORed with not y. That's a weird looking y. There we go. ANDed with z ORed with w. Okay, so that's conjunctive normal form and disjunctive normal form. It makes your life easier because a lot of the time, like, you start with a formula that looks weird like this, like x times y plus some giant thing like z, let's say z, z times w, I don't know, plus p, and then all that times a q, and then maybe like do some complement with this one, and then once you've done that and multiplied it by q, do a complement of the whole thing. That's disgusting. we would rather make it be in one of these normal forms that we kind of understand a bit better. That's the whole point of it, all right? So that's way too complicated, and we'd prefer to have our formulas in one of these two forms, these normal forms. Too complicated. And so those are their names, and that's what happens there. So let's see. With that in mind, here is my next question for you. Please draw a circuit that computes the function described by this input-output table. So here's x and y values. They're going to take some inputs called x and y, and you have to figure out what Boolean expression creates these outputs for these particular inputs. So like when x is 0 and y is 0, it has to give you a 1. When x is 1 and y is 0, then it also has to give you a 1 and a 0 otherwise. So like, what is this? What is this formula? Do that first, then you can convert it to a circuit. All right, so give that a try. All right, so here is again how you do it. You just look for the 1 columns essentially, or the 1 rows. You could also do it with the 0 rows, but you'd also have to negate if you did it that way. So this is an easy way to do it. So when is this one a 1? It's when x is 0 and y is 0. So when not x is true and not y is true. Put a 1 there. And it's also true here, so if that's not true otherwise, put a 1 when x is true and y is false. So x is true and not y is true. Okay? So that immediately gives you your formula that creates this function. That was one version of the function. And so this in Boolean algebra land, again, just getting practice with the notation, it's x times y bar, or x bar times y bar plus x times y bar. All right? So that is the formula, and then we can take either of these and create a circuit for them. So the inputs are, of course, just those two things, x and y, and it looks like I need to negate both of these eventually, or actually I never need to do normal y, I just always need negated y, but sometimes I need regular x, and then sometimes I need negated x. So like, let's do the left side first. So x ANDed with, or x bar ANDed with y bar. That is going to be an AND of x bar, there is its negation, and y bar. There we go. And then I want to OR all of that with x by itself ANDed with y bar. So there's another and that's going to be y bar some more. So let's take it some more. And then let's get x up in here as well. But before we negated it, you see like there's a concept of time with these circuits. And so we'll hop over this and then feed it into this AND here. And so now coming out of both of these, I have this first one is x times y, both of those bars first though, and then this one is x ANDed with y bar. And then I'm going to OR both of them, because that's the last operation, or plus, whichever one you want to think about. So here that is, boop, and up and out we go, and that is our final answer. This is coming out of this output wire is x times y, but first bar them both, ORed with x times y bar. All right. Hope you got that. Please yell at me if you did not. If there's any questions that you have about that, I want to make sure that that gets clear in your mind. So just getting some practice with the circuits, the new notation. And like all of logic, like this is essentially logic, you have the same laws for Boolean algebra, just like you had these same laws for logic formulas. All right, so like you OR the things, it's still the same, and the things, it's still the same. Associative laws, put the parentheses in whatever order you want. Commutative laws, it's just a new way of looking at the same thing. It's really all the same, all right? So with that in mind, like here's what De Morgan's law looks like. Here's what De Morgan's law looks like for AND and OR. Kind of cool the way it's new, but you know all of this already. You know these names. The notation is just the new thing. So take this slide, and here's a question for you. So using the laws of Boolean algebra, show that this Boolean expression is equal to this Boolean expression, and show every rule that you use. So take this and then use this, name each law / rule, and that will get you at your final answer. So you're going to start with, of course, x plus x bar times y and all of that bar, and then you have to come up with the other things, like eventually leading to x bar and y bar multiplied down here. All right, so give that a try, and I'll show you how I do it after you. All right, so the very first thing, like the outermost operation here is this complement, and I want to get rid of that. So I want to like distribute it between each side of this OR. It's going to be a De Morgan's law, remember? So it looks a bit weird, but it's going to be like negate this side, and change this to an and. That's De Morgan's law all over again. It's going to be this one. See it? So I'm going to negate the left side. I'm going to negate the right side, which is, well, let's do that in chunks. So like that's x bar times y. I need to negate that. Doing De Morgan's, which pushes that negation inward. This changes the OR to an and. That's pretty cool. That's what I have by De Morgan. And then, let's see here. Yeah, I think we need another De Morgan here as well to push that negation inwards. I would say that's a good idea. So we have x bar still multiplied by, and then this negation is getting pushed inwards, so we have the negation of the thing on the left, which is x bar, and the negation of the thing on the right, which is y. So we have x bar bar, ORed with, plus now, y bar. All right, so that's that. That's De Morgan. One more time, and then we have two hats here. Let's get rid of the hats by using the double negation law, double complement law, when it's Boolean algebra, because it's not called negation anymore. So that's x bar times just x plus y bar, and so that was a double complement rule. Complement. And then what else? Let's see here. We eventually need to get these like next to each other, like get the ands next to each other, get the x and y next to each other, because like this, if these two could be together, then we have an answer. And so we kind of want to distribute this because then x and with x bar, or x bar and with x, whatever order it's in, that's just always false, right? You can't and some variable and its complement or its negation and have anything other than false. Like one of those was true, the other was false, right? So that just makes falseness. So let's use, therefore, the distributive law. We have this one, I think. Multiplication distributes over addition, just like it does in normal math. Though the other way also works, which does not work in normal math, which is funny. So yeah, let's distribute this and among this parenthesized thing of ORs. So this is going to be x bar anded with x, ORed with x bar anded with y bar. And that is a distributive law. Distributive law. All right. And then we have x bar and x. And we can get rid of that if it looks like, let's be very precise, if it looks like this. If we have x on the first side and then x bar on the right side, then that becomes 0. So it doesn't yet look like that. I would give you full credit if you just went straight from here to use the complement law. But let's use the commutative law first to make it look exactly right. So this is x and with x bar. That's the same as this one because you can commute things that are multiplied. And is commutative. And then we still have x bar, y bar. That's the commutative law of and, or multiplication, I guess, in Boolean algebra land. And then this will go away with the complement law. We have x, we have its bar. One of those is 1, one of those is 0. You're forced, or vice versa. And then anything anded with 0, and one of those sides is 0, is going to be 0 total. So this is 0 ORed with x bar, y bar, anded together, and that's the complement law. And then anything ORed with 0 is just the other thing. And again, let's just be precise. Let's be like, all right, I have something ORed with 0 on the right. That's that thing. So I need to use it. It's the identity law. I need to get it in that form. So let's use the commutativity of addition this time. You can put the 0 on the right. Again, you don't have to be this fancy and pedantic if you're doing it on a test or something. But I just want to show you me following the rules exactly. That is the commutative law of addition this time. And then finally, this goes away with the identity law. Anything ORed with 0 is the other thing, right? Because the 0 is not contributing any truthness, right? It's just as good as saying the other thing by itself. All right, so that is the identity law. Is that how you got it? So hopefully my thought process made enough sense. That is how I would prove that using our laws/rules. And yeah, let me give you another example of this. So for this input-output table, give a Boolean expression that is a sum of min terms. So remember that a min term is a product of literals. Looks like this. These are options. So it's a product of either variables or their complements. And so give your answer back as a sum of min terms and is equivalent to this function f. So whatever this is. You have to come up with whatever that is. And so remember that sum of min terms, first of all, is saying DNF. The outermost thing should be or, sum. Asking for a formula in disjunctive normal form. And yeah, with that in mind, go ahead and convert this to a Boolean expression. Like, what is that? All right? It's got to be a sum of min terms, though. An or of ands. All right. So again, I like to look for the ones. There's a 1. There's a 1. And, well, what does it mean when this one's true? It's x is false and y is false. So x anded with y, but they're both false. X is false. Not x and with not y. So that's one side. That gives the 1 here. And then if I want the 1 here as well, that's when x and y are both true. X and y are both true. And if I want it to be true when either of these things are happening, then I want to OR them together. And so that process that I showed you before already makes you a DNF formula. That's great. Tells you exactly when it's true. These are min terms, and this is a sum of them. All right? And of course, like if you think about it long enough, this is really just the biconditional. It's the if and only if formula. But assume you didn't know that, this is another way to write it. Not x and not y, or x and y. Either way works. Okay? So hopefully that makes enough sense. I have one last question for you to try, and then that'll be it for today's lecture. So, all right, use those laws one more time of Boolean algebra, but this time convert this expression to DNF. So again, a sum of min terms. That's a very important one, because then you can just like read off, like, okay, there's a 1 here if this is true, there's a 1 here if this is true. That's why DNF is so cool. See if you can convert this, and remember, DNF is got to be a sum of products, sum of multiplications, essentially. All right? So, figure this out. Let's see. Before you start, notice that this is a one big bar over x times y. Notice that this right here. Notice. It is kind of hard to read given the normal logic notations. Notice this is x and y first, then bar. All right? And it's not. Because it would be a different thing if it were this. If it were x bar and with y bar. Those are two separate things. These are not the same. Let's do the and first, then the complement. All right? So with that in mind, see if you can convert this to disjunctive normal form. So an and of ors. Or, sorry, an or of ands. I'm getting my notation mixed up. So give that a try, and then I'll show you how I do it. Okay, so kind of, the idea is, as usual, like we'd like to push the and, or push the negations next to variables. So like these are not pushed next to variables yet, and these are not pushed next to variables yet. Like this bar is over a bunch of stuff, not just a single variable. Same with this bar. So let's push those inwards with some De Morgan's laws, right? So we started with x times y bar, and then we're multiplying that with x plus y bar. And so let's use a couple De Morgans to make this work. Let's do a De Morgan on this one. So that will give us x bar ORed with, or plus y bar. And then we're still multiplying with x plus y, all of that barred. All right, so that's a De Morgan. And let's do the same with this one, another De Morgan. So we have what we had before, x bar plus y bar, anded with, and then let's push that negation inward. It's going to be x bar, and then the plus flips to a times y bar. All right? That's pretty cool. Now we have De Morgan. And now remember our goal. Our goal is that we would like to get a bunch of pluses of multiplication. So plus needs to be our outermost thing. And so the idea is, well, here's a bunch of multiplication. That's fine. Let's make this plus the outermost operation. So let's make this plus the outermost operation, because that's the only plus we have now. And so the idea is going to be, well, this is a big thing that could be distributed to both of these pieces. You see that? And that would leave the plus on the outside and also put only multiplications on the inside. and that's exactly what we want. So we would like to put one of those here and one of those here with one of the distributive laws, and I think it's the one that has multiplication on the outside. So like x times y plus z is equal to xy plus xc, and you see how that is in, it's a conjunction of disjunctions. Cool. Alright, so that's our goal, and apparently to use the rule, right, it's got to be the thing that you're distributing needs to be on the left, so we can use a commutative law to put it there. But again, you don't have to be this fancy. But I'm going to try and use the rules as perfect as I can, as exact as I can. So that's x bar and y bar, ANDed with, and then this thing can go on the right when we use the commutativity of AND, x bar plus y bar, and that's the commutative law. And then finally we can distribute. So this one can go and distribute to both of these sides, following the rule, and so it's going to be x bar and y bar, ANDed with this thing, ANDed with x bar, plus, like all that's on one side, then plus, distribute that to the y bar as well. So it's like x bar and y bar goes next to this one. You AND it, because here's the AND, you're ANDing it with this one too. ANDed with y bar, cool, and that's another distributive law. Or that's the first distributive law for this example at least. And notice that now we have some minterms, so a bunch of multiplications, and then an OR in the outermost spot. So this is technically in DNF right now, so technically you could stop here, but this is kind of ugly. So we could stop here, but I'd rather not, because like you got a y, two y bars ANDed together, that's like stupid. Let's get rid of that. Let's make it cleaner. All right, so we could get rid of some of these y bars and also some of these x bars if we bring them next to each other. So let's use the commutative law to put two x bars next to each other, and then the same thing for this one. It's already there though. So that was a commutative law. Let us fix that, and then now we can use the laws that let us get rid of duplicates, and those are the idempotent laws. So could have just said x once. Don't do it. Don't do it twice. Unnecessary. So this will just give me x bar once, ANDed with y bar, plus x bar once, ANDed with a single y bar with, this is an idempotent law. Use. And then notice I have the OR of this thing with itself. So if you OR a thing with itself again, that's still the idempotent law. It's like, it's this one, but x is some big thing. That's just a single x still. No, you gain nothing by writing it twice. So this is just x bar ANDed with y bar. And this is technically in DNF still. Like I never got it out of DNF. It's just, there's no OR anymore. And that's as simplified as I can make it. Idempotent law one last time. And so that is the final answer, and I hope it makes enough sense. Please yell at me if it does not. But that was our first taste of Boolean algebra. It's just logic all over again, just with a different notation. It's wonderful, right? Very nice breath of fresh air after some harder topics. So that's where I want to stop today. We'll come back next time and finish up these slides, use fancier circuits, learn better how to like simplify things and stuff like that. Useful knowledge. Let's learn it in the next lecture. So I'll see you there.